Hello everyone and welcome back. In this video we are going to have an important discussion, which is we are going to learn about convergent and divergent improper integrals. Okay, in the last video we learned how to evaluate improper integrals. Now, unlike normal integrals, when you evaluate improper integrals, you do integration, but also at the very end you'll take a limit of the function, which is very different from what we do with normal integral problems, right? When you're solving a normal integral, sometimes you see integration by parts, integration by substitution or basic integration, but you don't take a limit of a function, right? But when you have an improper integrals, at the end of the day you take the limit of a function. Now that's very important, because when you take a limit of a function, you can come up with three scenarios. You can run into three scenarios. So a limit of a function, okay, can be either plus infinity or negative infinity. That means when you take the limit of the function, you get plus infinity or sometimes you get negative infinity, and that's bad, okay? Sometimes you might have seen this in your calculus classes, that when you take the limit of a function, actually the limit doesn't exist. Yes, there are functions where limit doesn't exist. And the nicest case is that when you take the limit of a function, it's a finite number. You get a finite real number. That's the nicest case. So actually when you're taking the limit of a function, you can run into one of these three scenarios, okay? All right. So in the last video, we saw two examples. We saw two improper integrals, where in the first example, see, this is the improper integral we solved, and we solved the integral, we took the limit of a function at the end of the day, and the answer is finite. I mean, e to the negative 2 is a number. You can use your calculator to find that number, but the bottom line is that that's a finite number. And we saw another example in the last video. When you evaluate the improper integral, at the end of the day, when you take the limit, you got plus infinity. Okay, so that can happen. Now, based on the answer that you get, you classify the integrals as convergent and divergent integrals. That means if you get a bad case, that means if you get plus infinity, negative infinity, or does not exist case at the end of the problem, that means your integral is divergent, not the limit, okay? The integral is divergent. So that means if the limit is infinity or plus infinity or does not exist, the integral is divergent. And guess what? If your limit is finite, then your integral is convergent, okay? Right. So to determine whether an improper integral convergent or divergent, you have to wait until the end of the problem. You have to solve the problem. At the end of the day, you look at what's the answer you got, you just make a simple observation, okay? If it is finite, then great, it's a convergent improper integral. If it is infinite or if it doesn't exist, then you have a divergent integral. Now we have to discuss what is the geometric meaning of convergence and divergence. What is the intuitive idea? All right, so to understand that, let's try to understand it from a picture. Now this is the function e to the negative 2x, okay? And let's look at the first integral. Now this integral is a convergent integral, by the way, convergent improper integral, because this number is a finite number. And the second integral, this is a divergent integral, of course, because the answer is plus infinity. Okay, so let's see what it means geometrically. Now the first integral says to you, find the area under the curve e to the negative 2x from x values 1 to infinity. That means find the area in this region, okay? Now the unusual thing here is that the interval that you're finding the area is infinitely long. We discussed this, okay? But when you evaluate this integral, you got a finite number. That means the area exists, right? Area is actually e to the negative 2 over 2, okay? Even though the interval is infinitely long, okay, the area is not infinite, it's finite. So that's what it means by a convergent integral. The area exists, area is finite. Now, how come this happened? Now, I mean, you can think about this. The area, the interval is infinitely long. How come area can be finite when you are finding the area over a long, infinitely long interval? Now, this is what happens. To understand this, we have to go back to the definition of the definite integral. How do we find the area under this curve? Remember, we divide this region into small rectangles, right? And we calculate the area of this each rectangle, and then we take the sum, right? That's how you construct the definition of the definite integral. Now, think about this. Look at the behavior of these rectangles. The area of each rectangle is getting smaller and smaller. That means you are adding the areas of smaller rectangles, right, when you are going along this infinitely long interval. Okay, so what's going to happen is that after a certain point, the areas of the rectangles are going to be so tiny, so small, such that it's not going to matter. The areas that you're going to add doesn't matter. Okay, it's so small that it doesn't matter. Think about this. If you are adding 0.00000000001 to 1, is it going to matter? No, it's still going to be pretty close to 1. Okay, so you can think after a certain point areas of the rectangles are going to be even smaller than this small number that I add. Okay, they are getting smaller and smaller. At the end of the day, you converge towards a one number. You get a one area, right? You stay around a one number. In this case, in this example problem, the area, this number that they are going to stay around is this number. Okay, so that's going to approach. Okay, so that's what it means to be an integral to be convergent, improper integral to be convergent. The area exists even though the length of the integral is infinitely low. Okay, now this valids for type 2 improper integrals as well. We only discussed about type 1 improper integrals in the previous videos, but this idea again valids for type 2 improper integrals as well. Alright, now before we stop this video, let's look at the divergent case. So divergent case means you are finding the area under the curve e to the negative 2x from negative infinity to negative 2. So that means you are finding the area, okay, in this region. So negative infinity to negative 2. Now you can see this region seems to be like it's huge, right? Now if you divide that region into tiny rectangles, the area of the rectangles are getting bigger and bigger, right? The area is getting bigger and bigger, so that you get the total area to be, the region is infinitely large, the area is infinity. Okay, so that's what it means for the improper integral to be divergent. If your area is infinity or negative infinity, I mean, or the area doesn't exist, or the improper the limit value doesn't exist. Now, what do I mean by doesn't exist in a geometrical sense? That means the area of these rectangles, sometimes they are big, sometimes they are small, again they are big, again they are small, so they are oscillating, so you never know what's going to happen. You cannot predict what's going to happen. So that's how you get the does not exist case, and that's how you get the divergent in does not exist case. So what's the bottom line here? You don't need to think too much about this. The bottom line here is that if you want to decide whether an integral is a convergent integral or a divergent integral, what you have to do is you have to solve the improper integral. Okay, write the correct definition, use the limit, evaluate the integral, take the limit, and take that final answer. So if your final answer is infinity or plus infinity, or if the final answer doesn't exist, then your improper integral is divergent. But if you get a nice number, nice means if you get a real number, any number, finite number, then that means your improper integral is convergent. That means the area exists. That's the area. Okay. All right. So that's the discussion about convergence and divergence of an improper integral. Thank you very much.